A todas y a todos ustedes les damos la bienvenida a esta conferencia magistral dada por el doctor Odell. A todos y a todos ustedes les damos la bienvenida en nombre del doctor Juan Silvestre Aranda Barradas, secretario de Investigación y Posgrado, del doctor Reynold Farrea Rebollo, director de Difusión de Ciencia y Tecnología, el doctor Luis Mendoza Álvarez y de un servidor, Ignacio Vega Acevedo, jefe del Departamento de Operación del Planetario Luis Enrique R. Con el motivo de la Noche de las Estrellas y en el marco del 30 aniversario del Telescopio Espacial Hubble, hoy tendremos la plática magistral impartida por el doctor Charles Robert Odell. El doctor Odell nació en 1937. Se formó como astrónomo en la Universidad de Wisconsin, donde obtuvo su doctorado en 1962. Fue científico responsable del proyecto del Telescopio Espacial Hubble de 1972 a 1983 en el Centro Marshall de Vuelos Espaciales. Ha estado en la Facultad de Astronomía en varias universidades, incluida la Universidad de Houston, donde fue profesor de astrofísica en Buchanan. El doctor Odell ha sido especialista en los campos de astrofísica observacional de nebulosas gaseosas y formación estelar. Actualmente sus intereses de investigación son la formación de estrellas en el cúmulo de nebulosas de Orión y la estructura y evolución de las nebulosas planetarias. Desde el 2000, el doctor Odell es profesor de investigación del Instituto del Departamento de Física y Astronomía de la Universidad de Barnard en Nashville, Tennessee, Estados Unidos. Anteriormente ha sido profesor de astrofísica en las universidades de Rice, Houston y de Chicago. El doctor Odell ha recibido diversos premios y distinciones, como la Orden a Mérito República Popular de Polonia en 1978, la de Medalla de Servicio Público de la NASA en 1991, ser miembro extranjero de la Academia de Ciencias de Polonia en 1994, el Premio de Investigación de Humboldt en 1996 y el doctorado honorario en Ciencias de la Universidad Estatal de Illinois en el 2001. El doctor Odell actualmente es miembro de las sociedades científicas profesionales como American Astronomical Society, la Universidad Astronómica del Pacífico, la Unión Astronómica Internacional y la Asociación Estadounidense para el Avance de la Ciencia. Es un verdadero honor y un verdadero gusto tener al doctor Odell. Dr. Odell, it's really a pleasure to be with you here, and you can start at any moment you want it.
Good afternoon. It is my pleasure to speak to you about my favorite subject, the Hubble Space Telescope, and the results that are coming out with it. In this first slide, we show this beautiful picture of the Hubble. And it says it's the 30-year anniversary of the Hubble. Now, as someone who has participated in it since 1971, this is the golden anniversary for me, because it took almost 20 years to build the Hubble Space Telescope. The Hubble Space Telescope is composed of many, many parts. These different parts, shown here in cross-section, were constructed in different parts of the United States, Canada, England, and Europe, and brought together in one place in California to actually build the observatory. For example, the telescope portion was built on the east coast of the United States. And after the telescope portion was complete, it was put inside this very strange looking airplane, which is called the pregnant guppy airplane. So the telescope fit inside and was flown from the East Coast out to the West Coast near San Francisco, and where it was assembled with its other parts into the telescope as a whole. Now, the telescope is about as big as a intercity bus in Mexico, which I am happy to say I have ridden many times, but it is not as big as the city buses that flex in the middle, but it's a big instrument. And here it's a fun picture because you see how it's being moved around between test chambers by people pushing on it, floating on a cushion of air. Now, the science of the observatory is done with individual scientific instruments. For example, this is the so-called wide field planetary camera, the camera that took most of the images that we see in the public immediately after the launch of the Hubble Space Telescope. Now, as I mentioned, 19 years in construction. This all came together on a beautiful day in Florida when it was launched inside the space shuttle. And the telescope is in here, the so-called payload bay. The telescope was designed to be as big as that payload bay would allow. And in the second day in space, the remote manipulator arm reached down into the payload bay, lifted out the telescope, and released it into space. But then a terrible thing happened. That is, we discovered that the images were not perfect, but the images of stars looked like they had a certain halo or corona around them. And the center of the image was sharp, but still not what we expected. And at that point, the Hubble became the laughing stock of the world. So here is a cartoon drawn by Gary Larson and the far side, showing space creatures, and another photograph from the Hubble Space Telescope. So a terrible time for us all. Now, as it turns out, we know what was wrong, something called spherical aberration. We learned about it right away, and we also learned the cause of it. That is, an alignment device that was used for testing the surface of the mirror was misaligned when it was assembled. So that once we knew what was wrong, then we knew how to fix it simply by altering the lenses in the subsequent scientific instruments that were installed. Now, how could this happen? How could this terrible mistake happen? The problem was the Hubble Space Telescope was built by people, and people can make mistakes. And supposedly, there are enough people checking on one another that the mistakes are corrected, but they were not. That is, people were not candid about the mistakes they had made. They were not suspicious of their own work. But once we knew what went wrong, what had occurred, then it could be fixed. Now, the images were still useful. And indeed, one of the first places imaged by the Hubble soon after launch was here in the heart of the Orion Nebula, which is a beautiful sight in the winter sky. When you look at the constellation, you see this fuzzy area and we know that this was an interesting area, and took 10 orbits of observations on this region, or correction, we made 3 orbits of observations to study this region in detail. This is a region of star formation. All of these stars here are very young. This is the gas left over from their formation. But by serendipity, we discovered something unexpected. Namely, when you look at a high magnification, you see that only a few of the stars look like what you expect stars to appear. But many of them had these dark disk around them. And what these are stars still in formation, collapsing from gas clouds down into individual stars, but they're still surrounded by clouds of dust and gas. And the dust that surrounds them blocks out the light from the nebula that is in the background. And it is this material, this dusty material, in a disk like this, from which planets form while the star is forming. And in fact, star formation and its planet formation are linked together. Sometimes when we look at these regions where it's almost flat on, it looks like this. Other times when that disk is seen edge on, it even obscures the nascent star down inside. That this glow of luminous gas around is the remaining gas that has been lighted up by the nearby stars. So a number of science projects and discoveries were made with the Hubble before the repair was made. But in December 1993, the shuttle visited the Hubble, and this time on a repair mission. Again, it was grabbed by the shuttle's arm here and now attached to the shuttle, but not brought into the payload bay. And then astronauts went out. This is a picture in orbit, went out into the shuttle and started replacing instruments and putting in some things that made it a better observatory. Now, we had always planned to do servicing missions. And in fact, when we designed the Hubble, we did test that. Here you see a picture of one of the tests, and we used the results from these tests of doing a simulated repair mission to help design the observatory. Now, this picture was made from a large tank of water with 2 astronauts weighted So they're like in C-G. You know that it is in water because you can see bubbles coming up from their helmets of their spacesuits. And you can also see a scuba diver down in the lower left. Now look how similar that is to a picture taken during the first servicing mission of the replacement of that same instrument in orbit. So it was all planned all along, and it worked. The repair worked. On the left, we see a picture of a nearby galaxy made with the Hubble before the servicing mission, with this camera down, precursor of this camera. But after this camera was inserted, then the same galaxy looked like this. So the observatory was now working as well as we ever hoped it would. There were 5 total servicing missions to the Hubble. Most of them, only the first one involved repairing instruments. But at each of these servicing missions, different new instruments that were more powerful than the original ones were installed, and even parts of the observatory itself, like the computer was installed, new gyroscopes for pointing it, more scientific instruments, more components of the observatory, more and better scientific instruments, and the last servicing mission, and new batteries and other components of the observatory. But then the science could start in a serious way. So let's first talk about scientific results from planets. Here's this beautiful picture of Jupiter. And you can ask, well, why build a telescope or use the Hubble to look at Jupiter? Because there are satellites going around Jupiter right now. The answer is you cannot see Jupiter, the entire Jupiter, at any one time. And where the satellite can view changes as it is in orbit. And this series of pictures shows the Great Red Spot, which is an enormous typhoon or hurricane that has been known to last for over the last 100 years. So this gigantic hurricane in the atmosphere of Jupiter, you can monitor with time, and you can see how it has changed over 20 years in this case. You can study Saturn, and here we have this beautiful picture of Saturn. Again, there are satellites going around Saturn today, but by viewing the whole thing, discoveries could be made. This slide shows both Jupiter and Saturn, but we have to understand them. We have to understand what the Earth would look like viewed from apart. We know that because the Earth has a magnetic field, that magnetic field guides electrons and positively charged particles coming from the sun and keeps them from bombarding us on the surface of the Earth, but rather it bends the path of these charged particles so that they come into the north and the south pole of the Earth. In Mexico, one rarely sees them, but in the far north and the far south, you see the results of these energetic particles striking the upper atmosphere of the Earth and forming the aurora borealis and the southern hemisphere. What was discovered is that Jupiter, with its strong magnetic field, does the same thing to take these particles that originate from the sun, a wind coming off the sun, and making it stream in to the north and south poles of Jupiter. Likewise with Saturn, it was discovered that the aurora occur there too. And these are important to understand. They're not just a curiosity, because understanding how these particles are streamed into the north and south poles helps us predict the behavior of these particles that strike the Earth. And the results of that can be very important in terms of power outages, things like that. Now, another part of planetary studies with the Hubble was entirely unexpected when we built the Hubble, because we didn't know for sure that there were extrasolar planets, but now we do. There are thousands of planets orbiting other stars that are known, and they're discovered as the planet crosses across the face of the star as viewed by the Earth. So the star blocks out a small fraction of the star's light and makes the star a little fainter. But if you take a spectrograph, a device for breaking light up into its component colors, you see that the atmosphere of the planet, shown here, in that spectrogram that results from breaking up the light into its component colors, the gas in the atmosphere of the star has left its signature in the light of the star. And so you can learn of the chemical composition and the conditions in the light of an extrasolar planet. Something very powerful, something we never expected when we built the Hubble. Now, we could do other things very early, like revisit the region of the Orion Nebula and map that region very accurately. Remember that this is a region of about 2,000 very young stars. That is about 1 million years or younger. And it's surrounded by this gas that from which the stars have formed. And it has these objects we call proplyds, those things that have the disk of dust and gas around them. So now we're flying, we can make a simulation because we've mapped the region, and we can see these proplyds where they lie within the nebula. And here's that nice one where the disk is viewed almost edge on. So the Hubble then allowed us to go back, study the Orion Nebula, and model it in detail. Again, that's important because this same process it occurs uniformly and universally in the formation of stars, because stars usually form in great clusters. Now, we see when we look at objects like this, the so-called pillars of creation, that some of the stars in this cluster have already formed and heated up the gas on the edge of these dark clouds of dust and gas that we see here. And if you look down inside there and on the edges of this object, you can see those same proplyds that we could see in Orion are here in the Eta Carini Nebula. You again see these great dark clouds of gas and dust from which new stars can be created. So inside there, we see these same proplyd objects. But once the stars are formed, they don't really look very spectacular because they're just stars. They look like stars. But what makes them luminous is their burning hydrogen fuel down in their interior, their center. Now, for a lower mass star, like our sun, or a little greater mass, the most common type of star, they will eventually use up their fuel in about 10 billion years. And the age of the galaxy is older than that, as is the age of the universe. So as the star starts to run out of fuel, it swells up. It swells up to be as large as the orbit of Mars. And when it does, when that happens, the stars begin to collapse. And here you can see a star that has used up its fuel and collapsed and spewing off its outside as it collapses. And this happens fast, over a period of 10,000 years or 20,000 years. It goes from being the size of the orbit of Mars down to being a white dwarf, where it has a size of the Earth. And it's so dense that if you could somehow take a sample of 1 cubic centimeter of that white dwarf star, it would weigh a ton. Now, other stars of slightly different masses, actually start to give off material slowly. And they kind of do hiccups as they start to get really big. And those hiccups produce shells of gas that are being expelled. This records a hiccup that occurred. Then you see that it had another hiccup. More recently, another hiccup, another still. And finally, it gives a big belch. And most of the material is blown off as the star is collapsing. Now, most stars are binary stars. And when a binary star runs out of fuel, it prefers to expel that gas from the atmosphere of the large star in a direction that's perpendicular to the orbit of the two stars that are nearby one another, going back and forth here. So it produced these fans of material. And this is actually quite common, that here's another star, object. The star is so faint by now that you can't see the pair of stars that produced it, but they are going back and forth here, and they have produced these plumes of gas. Why I included this picture is you see that it's dark here, and that's dust. That's dust that has been created in the star as it became very big. And that dust is expelled along with the gas in the outer atmosphere of the star. And that material, that dust and gas, is spewed out into the interstellar medium, the space between stars. And eventually that is clumped together into great clouds. They break up into smaller clouds. And that's what new stars and planetary systems are formed. So this expulsion of gas produces the fuel for forming new generations of stars. Now, if a star is much more massive than about 10 solar masses, its collapse occurs very rapidly. That is, in a matter of fractions of a second. Now, back in the year 1054 AD, a bright star was seen in the sky by Asian astronomers. And when we look today at that region, you see the gas that was expelled violently in this case to produce a supernova. In this case, the star collapsed to the point that it went right through where a white dwarf would be formed and formed a neutron star. Neutron stars are smaller, but approximately the same size as Mexico City. And if magically you were able to take a sample the size of a grain of sand of that neutron star, it would weigh 1 ton. Now, these supernovae occur frequently, that is every 100 or 200 years in our own galaxy. And the shells of gas that have been thrown off eventually get diffused out and become these beautiful supernova remnants. Now, none of these stars in the middle are actually related to that collapsing star, because the neutron star that was formed is just not luminous to see. Now, let's leap out in space and look at some of the results from galaxies. Now, galaxies come in a variety of forms. A very common form are the so-called spiral galaxies. If we were magically somehow able to fly out in space perpendicular to our Milky Way galaxy and at a great distance, we would be able to see it looks like this. It has a compact nucleus. By now we know there's a supermassive black hole there, and then these spiral arms, and those red splotches are regions just like the Orion Nebula or the pillars of creation or Eta Carini. That's where star formation is going on. Another type of galaxy is elliptical galaxy. Now, this particular one kind of has some of the characteristics of a spiral galaxy too. So this is an intermediate type. Now, a pure elliptical galaxy is shown here in Messier 87. And there you have no indication of a disk surrounding it. But we'll come back and talk about the very middle of this galaxy. So the Hubble is able to study nearby galaxies in great detail. The most famous, the closest spiral galaxy to us is Messier 31, the Andromeda Nebula. This is a ground-based image of it in the lower right of the slide. And the area with the lines drawn around is the area that's been imaged with the Hubble Space Telescope. And that picture is shown up here on the top. This is the largest picture ever made with the Hubble. And it was created from thousands of individual pictures made with its workhorse cameras. So with images like this, we can study things that go on in galaxies that in our own galaxy are hidden because the dusk in the plane of the galaxy. And of course, there are many other galaxies to be studied. And you see that many galaxies are found together and they distort one another by their gravitational forces. Otherwise, these galaxies would look like simple spirals. But now, particularly in the upper one, you can see how it has been distorted by the gravitational field of a neighbor. And galaxies can merge together, which is a very important part of the evolution of our universe. Let's go back to Messier 87. Beautiful object in its own right. But with Hubble, we discovered that looking down into the core of this galaxy, into a very narrow field of view, things really get interesting. Now the scale of magnification is much greater. So in that previous image, this core of the Messier 87 galaxy would have looked like a star. And you see this great plume of gas that's headed out from it. And that represents gas that's been expelled from the supermassive black hole down in the middle of this galaxy, formed by the merger of stars. And two stars stick together, more gravitational attraction, draw in another star, draw in more still, till eventually you have something that's many hundreds of millions of times the solar mass of our sun. But as this occurs, evidently it has a rotation. And it can spew off these jets of material from them. They're so energetic that they extend far beyond the optical picture of the galaxy. And you can see them in radio waves that are created. Now, with the assistance of Hubble, but primarily with radio telescopes, when you look with the finest possible resolution down in the center of that galaxy, you actually can make a picture of a black hole. Oh my goodness, did I just make a mistake in speaking? Because black holes, the light does not get out of it. But what you can do is see the gas that's being drawn into the supermassive black hole just before it crosses the event horizon. On one side of the event horizon, the light can get out, but on the other side of the event horizon, the light, any light emitted there can never get out and shares in this continuing collapse of material into truly an infinitesimal point. So the gas we see here is the gas that's being sucked down onto the supermassive black hole and then trapped inside it. It's continuously being replaced by gas from the interstellar medium of the galaxy. Now, there are other things we never envisioned doing when Hubble was built. We had a vague idea that galaxies, we knew that there was a magnetic field in galaxies like spiral galaxies like our own. And that, if you look at that magnetic field, you envision it, I should say, you can see it looks like the magnetic field of the Earth. This magnetic field guides material that streams out from the stars in the galaxy to form a halo of gas around the galaxy down in the middle. And if you take the Hubble and look through the halo of that galaxy at a distant quasar, and the quasars have a spectrum, that light after it's been broken down in a spectrograph. And just like we saw the signature of the atmosphere of planets when we looked at orbiting planets passing in front of the star, now we can see the signature of the gas that's in the halo of a galaxy. Nothing we ever imagined when we built the Hubble. Now, probably the most famous image made with the Hubble Space Telescope is the Hubble Ultra Deep Field image. It's composed of many hundreds of hours of images on the same field of view. You see, it's filled with objects, but only a few of them are stars. There's one and there's one. Those are foreground stars in our own galaxy. But everything else in this image is a galaxy just like our own. each one has some 10 billion stars in it. Some are large. You can even see the spiral structure here. Some and others are smaller and smaller, fainter and fainter too, until eventually they become very faint. So an object like this, which looks like a star, is actually a galaxy very, very far away from us. Now, a little physics lesson. Because light travels at a finite speed, 300,000 kilometers per second, when we look at the sun, the distance it takes about 8 minutes for the sun to reach us. So we are seeing the sun as it appeared 8 minutes ago. When we look at Jupiter, we see it as it was 45 minutes ago, the light travel time. We look at the nearest stars, and we see them as they were about 4 years ago. 4 years ago. The center of our galaxy, we see it as it was 26,000 years ago. That Andromeda Galaxy, we see it as it was 2.5 million years ago. That Messier 87 galaxy, we see it as it was 54 million years ago. So when we look out in space, we are actually looking back in time. And this is the only equation I will use in this talk. The Hubble Space Telescope is actually a clock. The difference is it's a clock that runs backwards, so that when we look nearby, we see nearly the present. When we look to large distances, we see how things looked earlier in the age of the universe. Now, here is a model that was made, a three-dimensional model of the Hubble Deep Field, the galaxies in the center of that image, where the individual galaxies have been had their distance determined, so we know where they're located. And you look back and you see something interesting. The galaxies are fuzzy. And this is because early in the age of the universe, as the galaxies were just forming, they were very fuzzy and had not become their characteristic shapes. Also, we're using Hubble for something that we did not fully anticipate, in that we're seeing galaxies through gravitational lensing. Einstein's theory of relativity says that if you pass a light ray close to a massive object, the direction of that light ray will change. And in fact, that was the technique that was used back in during World War II, a little more than a century ago, to confirm the theory of relativity. Now, when you look at this image, you see a number of bright and massive galaxies, a small cluster of galaxies. But you see many of these galaxies have these arcs of light like this that are distorted. This is shown better in this slide. So here's a cluster of galaxies with a dominant galaxy here in the middle. And what we were seeing here is the same galaxy over and over. And this galaxy lies in exactly this direction of this nearby galaxy. Nearby, in this case, means 100 million light years away. But this galaxy is located right in the same direction. So but it's not exactly there. So as the light from that distant galaxy enters the strong gravitational field of the massive nearby galaxy, it's bent in its direction. And so although the original direction was right there in the middle, this bent light, these Einstein images here, are seen off on the edge of the field of view. And this actually, and the distant galaxies are made brighter by this process. So it means that we can actually see and study galaxies that have been gravitationally lensed in much more detail than we would otherwise do. So lots of things have happened with the Hubble Space Telescope. But ground-based telescopes have been getting better during the same time. And some of them even image as well as the Hubble, but over very tiny fields of view. The radio astronomers have been busy and built this vast array of millimeter wave radio telescopes in northern Chile. And this image shows but a small fraction of all the telescopes. And now those can image in the radio with the same accuracy of the Hubble, but they cannot image optical light. Other improvements on the ground and optical telescopes have been made. And here I show a picture of the world's largest telescope in the Grand Canary telescope in the Canary Islands. This telescope is a joint adventure between Spain and Mexico. So Mexican astronomers helped build this, especially the instrumentation going into it. And they can share in the use of this largest telescope in the world. So advances are being made with ground-based telescopes. But advances have been made in the space telescopes too. A successor, in a sense, a successor to the Hubble Space Telescope is being built right now. It is expected to be launched in 2022. And that is called the James Webb Space Telescope. You see how much larger it is than the mirror of the Hubble. You see the telescope is much bigger than the Hubble, but it will only work in infrared, far red images, infrared. So the light colors we are familiar with are down here. And the infrared, our eyes cannot see it. The light does not come through the Earth's atmosphere. You have to go to space to observe it. It will not be in a low Earth orbit like the Hubble Space Telescope, but rather it will be located on the other side of the moon. Now, I don't mean the dark side of the moon, but rather 1.5 million kilometers beyond the Earth at a place called the second Lagrangian point. Since it's located there, it will essentially fly in formation with the Earth as the Earth goes around its orbit of the sun. And out there, that's the great advantage because you're away from the bright light, contaminated light of the Earth and moon. Here's a picture of the Hubble, the James Webb Space Telescope. A very different design. It's than the Hubble. Its scientific instruments are here on the side that's facing the sun where they can be kept warm. The mirror needs to be very, very cold. So there are these sun shields, a multi-layer of shiny fabric that reflect all of the light from the sun, Earth, and moon. And so the telescope becomes as cold as deep space. And that's why it's located so far away from the Earth. It will be complementary because it's an infrared telescope to the Hubble. But how long will the Hubble last? Well, we hoped when we built it that it would last as long as 10 years through servicing. And after 10 years, we were asked, well, how long will it continue to operate? And we said, maybe another 5 years, bringing it up to 15. At the 20th anniversary, the same question was asked, how long will it last? Again, the answer is 5 years. Now we're at 30 years. Again, the answer is probably 5 years, maybe longer, because at this time, almost all of the systems on the Hubble Space Telescope are working. And the few parts that have failed have redundant components. That is, it was built with multiple things like the gyroscopes. So, and we learn more and more about operating the telescope with time so it can operate with fewer gyroscopes. So that will probably be what will limit the lifetime of the Hubble. So it's in good shape, it's scientifically more powerful than it's ever been. And don't you love a story with a happy ending? Thanks for allowing me to share this story with you.
Dr. Odell, thank you so much for this talk. It's really interesting to know about all of this. If you wish or you want to take some questions for our audience.
I will be happy to. Let me point out that I had trouble with the cursor. You probably noticed that, but at this point, it's too late. Okay, I'm happy to answer questions.
Of course.
Am I going to be on camera? Will you be recording my image while I answer the questions?
Please, just now we are looking at your screen, not your camera.
Okay, so I will stop share.
Excellent, now we're seeing you. So if anybody in the audience want to make some questions.
My question, Dr. Odell, is I am Hector Castañeda, as you know. And my question is, now, from the technical point of view, the engineering point of view, what do you think that it was the more difficult section or area of the telescope when it was built?
What was the most difficult thing to build?
The more technological from the technological point of view, what was the more hardest part to design and build?
The pointing system, because you have to keep the telescope pointed very precisely at a star or a galaxy during the exposure, the time exposure. But before that, you have to get it pointed to the right part of the sky. And that's done with something they call star trackers that look at the position of bright stars and get the approximate position. Then you transfer it to a system, something called the fine guidance sensors, which locate the stars very precisely. And then once it's pointed, the gyroscopes, the very precise gyroscopes there are what control the telescope. And indeed, because we recognize this was the most difficult part technologically of the observatory, when the primary mirror, Senor Castaneda, there's a cat on the top of your bookcase. I wanted to point that out. That when we were testing the primary mirror or putting together that testing device, we were having problems and we had to redesign the pointing system. So that diverted the attention of everyone. We thought the testing of the mirror would be simple.
Thank you very much, Dr. Odell, for your question, for your answer.
We have another question from Dr. Fuentes.
Yes, thank you very much. Dr. Odell, thank you so much for such a wonderful journey, crossing all scales of the universe using HST images. Thank you very much. I have two questions for you. The first one is, do you have a favorite Hubble image? And my second question would be, which HST result has been the most relevant for your field of research?
For the field of?
Research, of your field, the field of where you work for the interstellar medium research.
Of course, it is like you ask me which of my children that I love the most. I would say, of course, my Orion images, I think are very, very important, and they're usually listed in the top 10 when they play that game of of what are the most popular and informative images. But I have to say that the Hubble Deep Field is probably the most significant image that has been made by the Hubble. That is, it has stimulated so much work on the large-scale structure of the universe, not only using the image itself, but giving ideas for other fields of investigation of galaxies. So I really answer both of your questions at the same time now, and except that in my own field, which is the study of gaseous nebulae, that I would say that the work on planetary nebulae, these lower mass stars that are spewing off gas, have really improved our knowledge of how the process by which this gas is being expelled by the stars as they collapse to be from supergiant stars to white dwarfs. So those shells, shells that I showed in the one image of, which I said when the atmosphere of the star had hiccups, there was seeing that in vastly greater detail than we've been able to do from the ground. And you can reverse engineer the image to figure out what was going on in the atmosphere of that red supergiant, say 20,000 years ago.
Thank you very much.
Let me say, it's just fun for me to share this story with this particular audience, that is with a Mexican, primarily a Mexican audience, because I've been lucky that ever since I, immediately after I got my PhD, there have been important scientists in my life who were working and from Mexico. And it's been such a pleasure to see it start with just a handful of people, all of whom had to be sent off to the United States or to Europe to be trained. And as those people returned to Mexico, it created new jobs. It created what in my area of astronomy, interstellar medium, the Mexican astronomers are, they're right at the top. And as a secondary effect, Spain caught up, has started to catch up with Mexico, which would never have happened if Mexico had not done it first. And of course, I've been to Mexico many times, not enough times, but I've been many times, and I'm familiar with the people, the institutions, what make it such a wonderful society.
Thank you very much, Dr. Dell. If you are okay to take one more question.
If there is one.
Dr. Hidalgo.
Hello, good afternoon, Dr. Dell. How are you? I hope you are fine.
It's nice to see you again. And I am even more deaf than the last time we have seen one another. So please speak slowly.
Okay, I will. I'll try.
I know it's hard for you to speak slowly.
Yeah, you know me. Thank you very much for this beautiful and very interesting talk. Really, it's just amazing. I love the picture, but I also love the talk. You know, the thing that you said about this picture. I have not two questions, but one comment. I was very surprised when you say that the lifetime for HST will be maybe another 5 years or more. So it means that it won't be shut down, because I always thought that when the James Webb were up there, the Hubble will be shut down. But you said that it won't be. So it's a very happy end.
Yes, I'm glad to pass on good news. And by now, since we have no servicing missions planned, the operation of the Hubble is not very expensive as compared with the Webb. It's less than $100 million a year, and it's dropping, you know, every year. It's less and less expensive as people become more experienced. So it appears that we are in no immediate risk of running out of funding. Now, the critical time will occur when we're down to one pointing gyroscope. At that time, the efficiency of the telescope will be reduced to about 50%, unless the decision is made to study some special fields of view for very long periods of time, because the inefficiency is because it takes a long time on one gyro to move to, say, one galaxy to another. But when that happens, then, you know, the money people may say, well, this is not good. It's not worth it. And then I would like to think it's really up to the scientists. If they think it's still worth it, then there will be enough hue and cries of pain, that it will stay alive until that last gyroscope fails. So, good news.
Absolutely good news. I mean, the other question is, do you have anything, what do you expect from James Webb? Because it will be is much larger than HST in the infrared. I think that we very, very exciting discovering are coming or not?
Well, of course, the people who do cosmology are delighted, because, of course, this optical light we're working with is, you know, just highly redshifted. Most of the light has been shifted into the infrared, so we're only seeing a small fraction of the light that's being emitted. So those people are delighted. The star formation people are delighted too, because you just look at what we see in Orion. All of these objects that are obscured will now become visible. So I think it will, you know, primarily be a study of star formation and deep space. Thank you for your question.
Thank you for your answers. Thank you, really.
De nada, de nada.
Any other questions? No? Dr. Dell, any last comment you want to do? Anything you want to say to these younger people from Mexico, the younger scientists from the future?
Well, it's for young people, it's very common to become interested in astronomy, especially since you can Google all these beautiful pictures generated by the Hubble and other things. But lots of people, young people, kids, middle school and even younger, become interested in astronomy. And because it seems accessible, you can see these beautiful pictures. Now, very few of them will actually end up being astronomers. But most of them, or many of them, will end up as scientists of one type or the other, because through the study, their interest in astronomy, they start to learn about how science works. Then as they grow older, they see that, hey, other fields, the mysteries of the universe are equally interesting, but they have started thinking about science and not about what you can do with a Game Boy. And so that's, I think, a great advantage of interest in astronomy. Very few of us are lucky enough or narrow enough in our vision to stay with it all of our life. I began, in the 6th grade. So I think that's the great advantage of learning about astronomy, because it gives you a base. As I say, most people are scientifically interested will become something else besides astronomers, but almost all of them will become taxpayers. And at some point they will be asked to approve the use of their tax money to support a relatively handful of people like you, I, all the questioners, the professional astronomers, to support a handful of people and to build a handful of telescopes to answer the questions that these taxpayers think are interesting.
Dr. Odell, that's very nice to you. It was a pleasure to hear your talk. It's a nice presentation. 10 years ago, 9 years ago, when I saw your presentation in EPN, I was inspired for that. And now I'm working in this. It was amazing. Thank you so much for your time, your patience, and all the effort you made to do and give us this amazing
and
conference.
Thank you for making this happen.
So just let me read this. It's por parte del Instituto Politécnico Nacional, a través de la Dirección de Difusión de Ciencia y Tecnología, le agradecemos al Dr. Odell por esta conferencia magistral. Y por supuesto, le agradecemos a todas las personas que están viendo esta transmisión a través de la red y los invitamos a seguirnos en las redes sociales. Fue un verdadero gusto y un verdadero placer tener a tan emérito investigador, astrónomo, y que nos pudiera dar esta plática a esta comunidad politécnica. Muchísimas gracias. Dr. Well, it was a pleasure. Thank you for the Instituto Politécnico Nacional, also from the Direction of Diffusion of Science. Thank you so much for giving this talk. And we are really think it's amazing to hear from the people, from everybody, to hear how the Hubble works, what's happening in the first years, the first moment you saw that something make mistakes and the people made mistakes. Thank you so much. So it was a pleasure, Doctor. Thank you for your time and your conference.